same as we saw with cobalt. So basically we have, again, just we have decarbonylation. We generate this 16 valence electron complex here. Well, actually it's maybe slightly different. Alkene coordination, right? Insertion, alkene insertion into the hydride. CO attaches itself to it. Migratory insertion. And then this reaction with hydrogen, reductive elimination, we form the product. Okay, now, so you see it's always the same in catalysis. Remember the second lecture was all those things that we had, all those elementary reaction steps. It's always one of those. If you know them, you have the tools to do catalysis. Because the mechanism is always the same. We'll see that in the CC coupling lecture as well. It's always the same. Okay. Now, basically, this is a great starting material because what can you do with this? You can play around again with the phosphines. And what I want to just sort of mention now is sort of recently, it's been quite popular to use so-called bidentate phosphines because, of course, what you have here, I mean, if you react this guy with a bidentate phosphine, you're going to get displacement and you're going to form a different catalyst precursor. And that's what scientists have done. So these are some phosphines. They have funny names, Bisbee, Bisbee star, Natphos, and Zatphos. Those are just sort of the names scientists have given them. These are typical phosphines used in rhodium-catalyzed hydroformylation. And you can see that the turnover frequency is not really that affected, but you can see that you have dramatic changes in the linear to branched or N to iso ratio. So this is basically just the unmodified, or let's call it the unmodified system. So this guy is the first entry here, PPH3. That's the ratio. So they've thrown in extra triphenylphosphine. You can see you've got about 10%, well, 10% branched aldehyde. Okay. And what you can actually see here is that you can dramatically switch the selectivities around, right? By changing the ligand. Now, this Xanthos ligand, right, is sort of considered a benchmark ligand, okay? It's considered a benchmark ligand. And to sort of just end things off today, I don't know what's going on here. I just thought I'd present some of my own results. So this is in fact the last bit of work I did in Berlin, and actually we've just finally submitted this paper. So check out what we did. We took exactly that guy there, right, that I just presented to you, which is a generic starting material for rhodium hydroformylation, and we synthesized new ligands. So this is the Xanthos, right, with phosphorus coordinating, and we made this guy here. So this X is silicon. So two silicon sensors, so now something different, not phosphorus but silicon, but isoelectronic. And if you do the reaction with this ligand, right, this is with silicon and germanium, look at, for 4 silicon, we have quite a high turnover frequency, check it out, 2621, and with Xanthos 3B, it's 3007.
That's temperature.
Sorry, I made a mistake here. X is 4.
If you go the other 4, it's 9,000.
Yeah, if you go 2 lines down.
Oh yeah, sorry. Well, that's embarrassing. I just submitted this. Okay, so let's look at 100 degrees, right? 4 and 5, that's silicon and germanium is absolutely useless, so forget about it. But silicon is really good, 9,000, right? And 3B at 100 degrees, 3,000. So we've got a much higher, 3 times higher turnover frequency, right? But the disadvantage is we've actually got quite a poor linear to branch ratio, right? 75 branch. But, you know, the fact of the matter is that it significantly improves the activity. And do you know why? Because it comes back to that whole picture we just had with Tolman. Because these silylenes, they're called silylenes, are very, very strong sigma donor ligands. So it increases the electron richness at the rhodium center, and that's why we have a higher activity. So it kind of makes sense, right? And that's what scientists are doing. They're always trying to make new phosphines to do new types of hydroformylation. This is just an example of work that I've recently done. And you can see that the conditions we used 50 bar pressure, and we also did it with some other systems to compare. That's a bidentate phosphine there, that's a monodentate silane. So, I mean, hopefully it gets published quite soon, and we've submitted a patent. Now, the thing is that the overall take-home picture is, right, cobalt hydroformylation, understanding the mechanism, the steps, realizing that you can take the cobalt system, throw in phosphines, and by using Tolman cone angle and electronic arguments, you can more or less somehow draw some conclusions as to how you can steer the N-to-iso ratio and how you can steer the rate of the reaction, which seems to depend on what? Sterics, the cone angle. Whereas N-to-iso is a little bit more difficult to delineate, but it seems from the data we have seen to depend, and that is sort of the prevailing sort of theory, it seems to depend more on the electron donor capacity than it does on sterics, because we see, you know, a whole distribution over there. And the third thing is you can do it with rhodium. You can do it with rhodium. This is a classic example of a rhodium hydroformylation catalyst, which works great. But you can actually functionalize it with other phosphines, as we did with cobalt, and literally thousands of papers have been published in this regard. Now, the important thing is this is a very important industrial process. You know, people don't just do it for fun. And it's because you take alkenes, which are a relatively cheap feedstock, which we can, for example, generate by Fischer-Tropsch. Remember, starting from syngas, you can make alkenes. And if you then take those alkenes and you do hydroformylation, you can make aldehydes, which can then be used for a range of different industrial applications, right? And basically, there's a couple of important processes still using cobalt. Now the problem with rhodium, although the reactivity is so much higher, 100 to 1,000 times higher than cobalt, is very expensive. So industrially, cobalt is typically used. There are three important processes: the OXO process from BASF, right? The Exxon process, and the Shell process. These are just different processes used, you know, slightly different reaction conditions, different catalysts and so on, all based on cobalt. And you can see they sort of have different ranges. So here you convert higher alkenes. Well, this is also sort of in the same range. But in the Shell process, they use phosphine ligands, right? And this is to a very large extent thanks to the work that was done by Slaw in the 1960s. Right? It was around that time, I think, that Shell developed this phosphine-mediated hydroformylation. All right. So that's the take-home message. And yeah, are there any questions?
Do they use iridium as well?
Iridium.
Yeah, because cobalt and rhodium.
That's a good question. I'm sure it would work. I don't know if anyone's actually done that. I'm sure someone would have tried that, but it doesn't make much economic sense at all, because with rhodium you get great activity and selectivity, right? And there's so many ligands available that, you know, if you want to publish something in this area, people have moved away from phosphine, so they're really coming up with novel, innovative ligands like we did. I mean, this is not self-glorification, but I mean, this is really a new family of ligands, and it's never been used in hydroformylation. So that's sort of how we sold our work. You know, it's silicon-based ligands, and they outperform benchmark systems like Xanthos. So this is Xanthos. And yeah, I mean, I think that's quite a comprehensive overview then of hydroformylation. So we're making a lot of progress, right? We've looked at heterogeneous processes and how they work in detail. We've looked at polymerization and stereoselective polymerizations. We've looked at, in detail, at alkene and alkyne metathesis and looked at its applications in natural product synthesis. And now we've looked at hydroformylation. So we're building up a toolbox of catalytic tools that we can employ in synthetic chemistry, right? That's the point. And by the end of this course, you're going to have a whole lot of tools that you can use going forward when you're a graduate student. Let's say you end up doing organic synthesis, doing very elegant stuff using catalysis, right? And so I think that's what's really great about a course like this, is it really shows the overlap between organic synthesis, industry, and homogeneous catalysis. And the lecture that we're going to do next is going to be CC coupling reactions. Very important, very, very important in organic synthesis. And we're going to look at it all from, there's two ways of doing it, either looking at one or two of them in detail. I've decided to take the broad perspective. So we're going to have an overview of CC coupling reactions mediated by palladium systems, so that you know you can make CC bonds in your dreams. Are there any questions? All right. So let's reconvene in 10 minutes, shall we?
Should I stop it? Should I stop the camera? This one?
Yes.
Oh no.